Hello everybody and welcome to another data recovery video. This time I'm working on a SANDISK Extreme Pro solid state drive that is not detecting. And if you're new to the channel guys, welcome. I am a professional data recovery engineer. People mail me in SSD drives from all around the country and it's my job to get the data back. Now this one has been mailed in from the Sunshine Coast, Queensland with not much description except for it's not working anymore. So let's take a closer look and see if we can solve it and get all the customers' data back. So let's plug it in and see what's happening. We'll check with the thermal at the same time and it's drawing barely, well, just 100 milliwatts. So one of these it's working. So this SANDISK, what is it? Extreme Pro should be drawing about 1.3 watts and this is only drawing 100 milliwatts. So a huge problem there, something with the electronics. So let's have a look under Microscope. This one's powered by a Marvel 88SS9187 controller chip. And it should be showing a lot more thermal activity than that. That was barely glowing at all. So something's wrong with the electronics. And if we have a look around, let's see if we can figure something out. Now straight away, we can see some corrosion on the electronics. There is some nasty corrosion up here, all around here. Look at these capacitors in here. They're corroded quite badly. In here's quite badly damaged. We can see corrosion coming up here. That shouldn't be there. And let's keep looking. So this is kind of power regulation. These chips here are the memory chips on this SSD. However, they look okay and the electronics look fine. What's under this sticker? That looks okay there. All the electronics around here look fine. And we'll just have a look on the other side. The other side is completely clear. There's no electronics at all. And it looks in good condition. Because this SSD, the SANDISK Extreme Pro, or really any SANDISK SSDs are quite common to be mailed into us, we've got some basic electronic test points to use. So first thing I'm going to do is check up here for our 5-volt input. Do we get it? Yes, we do. And we're just going to tag it down to here. Yes, we're following it there. Following it into here, and we should follow 5 volts into here. So we're getting our 5 volt input working. Now, we should also be getting 5 volts on these two corroded capacitors. Very important, so let's have a look. It's a bit hard to get a good test when it's corroded that bad, but yes, we got our 5 volts. Both of these should be 5 volts. Now we're going to move down to this inductor here. Now we need to check these 3 chips here. They've got a marking of SBV and they're step-down converters with different voltages. So looking at our test points and schematics we made, this one should be registering about 1.1 volts. That is correct. Then we come down to this one. What was this? 1.8. We're getting 1.8. And we come down to the bottom one and our schematic says 3.3. And we're measuring that. Yep, and that's within spec. So the next one we need to check will be over the other side, which is for this controller. Now, if we saw the thermal, we weren't getting much activity there, and it should have been glowing nice and hot with plenty of activity. So we're going to check this one up here, and it's going to be 2.5 volts. So to check it, it's going to be very hard to get inside this little pin here. And we're getting barely 1 volt. In fact, we're getting about 0.43 volts. That is a huge problem. And if we zoom in a little bit tighter on this little chip, we can see a marking of 3XT. It says 4Z at the bottom, but that doesn't mean much. We see different codes down there all the time on all these different SSDs, but definitely 3XT is something we've seen consistent with these models. If you even look around, what do you guys think? Does that look a bit corroded to you? It looks like something's happened in here. Some kind of corrosion has occurred. Even this shiny solder there, that's a bit unusual to see that. So it does look a little bit suspicious around the chip. Maybe it's corroded, I'm not sure, but maybe it's been short-circuited, blown up. Well, it's not short-circuited, I don't think. What I'll do is remove it out of circuit and see if we can get another one or something to fix this SSD. So we'll get in here nice and tight with some hot air to remove it. Just want to take our time. We don't want to break it, so we want to get the heat inside this chip. And take it out of circuit. So we just got to remember that little dot. If you can see the little dot on that chip, yes you can at the bottom right, it lines up down here. Which, is that a silk screen? No. So I'll just check the electronics around this area for any short circuits while it's out. I'm assuming in here would be ground. Here the beep, yes it is. Up this top right corner looks like it also goes to ground. And I think this is the output pin here, there's nothing there, and this side must be our input side, and everything around is okay. So I'm just going to check the voltages with it out of circuit. So with that chip removed out of circuit, it's still drawing 100 milliwatts, and the input side here is 3.3 volts, the output is 0.5 volts, which is the same. So whatever this little component does, it's not getting up to voltage. We're just going to clean up this little footprint a bit better. Make it ready for soldering a new one. Okay guys, so we've just hit a huge problem with this SSD data recovery repair. I've just gone through all my inventory looking for a spare part, for a spare chip for this, and I do not have anything in stock. Unfortunately, this little chip, 3XT, there's no part number for it. It's not a common part you can just ring up an electronics supplier and order. It's something unique and specialized and only really known to the engineers who built this. So I've just gotten off the phone from the customer and I've told them the situation, and they've told me that I must get this data recovery done by tonight. They said it's urgent and all the data on here is for a wedding, and I have to get this job done, completed tonight. What would be more ideal is if I get a donor SSD, but there's only one available for sale and it's in America, and that could take up to 3 weeks. The customer said, no, we need this data back by tonight. So the only other option I have is to homebrew and make my own chip voltage regulator that will do the job. It's a little bit riskier, but I've got no choice. It's the only way I'll get this done by tonight. So here we are on our local electronics Aussie suburban parts store. This isn't sponsored by them by any means. It's just someone I use for a lot of common electronics parts. They have stores all around the country, so I'm just using them for now. So we're going to look for a voltage regulator and see what they have in stock. Okay, so one of the problems we have here with common components, I mean, they usually sell what's known as jelly bean components or common electronics components. I'm going to have to find the best thing I can to get this SSD to work again. The biggest thing here is these fixed voltage regulators. They're fixed to 12 volts and I need 2.5 volts. So no, can't use it. Fixed at 15, can't use it. I don't know what that one is. We'll come back to it. 100 milliamps, and even at that may not be enough current, enough load to power the controller of this SSD. It's fixed at 5 volts. Too much. Fixed at 3.3 volts, 100 milliamps. You know, these are probably for voltage references, not actual regulators to provide a load, so that's a big thing. I can't use this, 5 volts. We got LDOs, low dropout linear regulator. Something like this will do. What is that? Oh, this is the 1117, so that's one of the most common ones on the market. I think we'll come back to that. And what else do we have here? No. Okay, here we go. 2.5 volts voltage regulator. Perfect. Let's have a look. And it is a LM336Z. Let's check the specifications for it. Current rating, 10 milliamps. Not even close to going to be able to do the job that we need it for. 10 milliamps is really just for voltage reference. It's not to provide any load like powering a SSD controller. So no, it's not going to work. 2.5 volts. But the voltage is correct. What do we got here? Okay, 12 volts. Here we go. Common ones again. 15, 24, 15, 24. Not even close to what we need. 5, 5. These are all fixed voltages, 6 volts. So 2.5 volts is not a common voltage that anyone's really going to need from a suburban electronics parts store. So we're kind of asking for a bit of a unicorn part here. No, not even close. So let's go back to this 1117. Here it is here, 1117, and see what they have in stock, because they have these fixed in all voltages, including 2.5. It's the most common one out there. Let's have a look. It's a low dropout voltage, 1.25 volts at 1 amp output current. Plenty to power this SSD. On-chip thermal, 3-terminal adjustable. So this one is adjustable between 1.2 volts and 5 volts. This looks like this is going to be the only thing available for me to use to get this data back. What do we got here? One regulator, input 15 volts max. Minimum output 1.2, maximum is 13.75. The voltage dropout is 1.25 volts, and a little milliamps draw to run it. This is an adjustable one, so it's basically the Swiss Army knife of linear voltage regulators, and this is the only thing that I can get to get this job done today. So I'm going to head down to the store and hopefully I can get one. It's going to cost me $1.10 to get this SSD working again. Let's go. And here she is. We have ourselves an adjustable low voltage dropout, LDO, adjustable voltage regulator. So we're going to set this to 2.5 volts so it can work with this SSD. First thing I'm going to do is prime solder on all these pins, so it's ready for me to solder jumper wires and the likes to it. If you look at the part number, it doesn't say 1117. It's probably from whatever factory. So many people make the same part number and knock off the original, but hey, whatever. I need it to get the job done now. So this is the data sheet for it. I will need it so I can figure out what the pinouts are and what I need to do to get it to work. You can see they make them in different output voltages. However, this one is the adjustable voltage regulator. That's all they had in stock. Applications, PC, motherboards, LCD monitor, graphics cards, DVD video player, NIC or a switch, telecom equipment, ADSL modems, printers, and if you want, guys, at Diodes Incorporated, you can add SSD, solid state drive, data recovery to this list. Now we've got a pinout, yeah, all the same. So we've got the adjustment pin here. If this was fixed, it'd be a ground pin, but this one's the adjustable model, so it's got the adjust pin 1. The output voltage is pin 2 in the middle, so we've got to remember that. The input pin is number 3. So we do need, and voltage output is also here. Okay, so on the back. So this page here is critical for me to understand how to get this to work for what I need it for, which is simply any voltage in and 2.5 volts out. So we've got our pin 3 input, we've got our pin 1 adjustment, and our pin 2 output again in diagram here. So what we're using here is 2 resistors, and I can tell this is one of the most common things in electronics engineering. It's a voltage divider, so you need a minimum of 2 resistors and you can divide the voltage. What is happening with this voltage divider is it's providing feedback to the adjustment pin so that this little chip knows how to output the voltage that I want. And it depends on this algebraic equation, which I'll zoom in for you guys, on how we're going to achieve that. And if we have a look at this equation, it's really just Ohm's law. It might look a bit confusing if you haven't seen a voltage divider maths before, but this is actually quite simple. We just need to plug our numbers in so we can get our resistor values. Now, voltage out, we know that. I want it to be 2.5 volts. So the voltage reference with the little star, because that star is going to link in this data sheet, which we already saw at the start, is 1.25 volts. Now that's what they've done. They've got something inside with a voltage reference of 1.25. Now we've got 1 plus R2. That's resistor number 2, which is this bottom one, R1, divided by R1, which is resistor 1. And then they've got plus I. So I is a symbol for current. If you remember Ohm's law, V equals IR. And they've got the adjustment current multiplied by R2. And the reason why they've got that, we'll have to zoom out again. They're plussing the current that this actual adjustment pin draws. So this regulator will draw its own bit of current. And depending on what resistor you use, which is R2, it'll also it'll manipulate the voltage output. So you've got to be careful with that. I'll explain that a bit easier in a bit. Now the other thing they want me to use in this diagram is a capacitor on the input, 10 microfarads. And there's another capacitor here. If you forgot what your symbols look like in electronics, that's a ground and that's a capacitance. 22 microfarads on the output. That's to help stabilize the voltage it produces. So what I've done is written the equation out. I've just kind of changed it a bit to make it a bit easier so I don't scare anyone away, so you can understand how fun maths and electronics really is. And it is simple. This is simple once I show you what's happening here. So we've got our equation. We just need to plug our numbers into it now. So our voltage out, we know we want 2.5 volts. Our reference voltage is from the manufacturer inside this regulator, and it was 1.25 volts. Now we're going to multiply it by 1 plus R2 over R1. Now that's what we need to figure out. And I'm going to cheat with this maths here. Plus the current of the adjustment pin, it draws current to figure out what it needs to do, times R2. What I'm going to do is I'm going to pick resistors so that this doesn't even matter. So I'm going to delete this. This is for precision, so I've just simplified the equation. Again, that would be for a lot of precision, or if you get the resistors too high or too low, that can affect you. But what I'm going to do is simplify this. So here's a lot of the common resistors I have. This is just a standard set of common resistance values from a E12 or E24 set. Look that up if you don't know it. And basically, we've got R2 divided by R1 plus 1 multiplied by the reference voltage. Well, there's something simple here, right? If I use R2 and R1 with the same value, then that number divided by itself will be 1. So it'll be 1 plus 1, which is 2. 2 times 1.25 will literally give me my output voltage I want, which is 2.5 volts. So now I only need 2 of the same resistor value. It really doesn't matter what I choose. It's going to be a division of that value by itself to give me 2. I could use any 2 of these resistors, 467 kilo ohm down to a 100 ohm resistor. If that's R1 and R2, 100 divided by 100 is 1. 467 kilo ohms divided by 467 kilo ohms is 1. So it doesn't matter. I just need to use the same resistor on the top and the bottom. But there's a trick I need to be careful of. If the resistance value is too high, it will create a lot of load on this equation here, and that'll interfere with my output voltage. And again, if it's too low, well, it'll waste a lot of power. So I need to try and find that sweet spot. What I'm going to do is keep things very simple, and I'm just going to use a 1 kilo ohm. So it should be high enough to not waste current, but low enough so it doesn't interfere with that the adjustment pin voltage, which will affect this. So let's use 1 kilo ohm. And to finish our maths homework, we'll do 1 kilo ohm divided by 1 kilo ohm for R1. Well, that's 1 plus 1, which is 2 times 1.25, and that gives us our 2.5 volts output, and that's how we're going to get the data back from this SSD, hopefully. Okay guys, so here's our store-bought electronics from the local parts supplier we're going to use to get this to work. Time's running out. I've only got less than an hour in the day. It's been a long day at work to get this to work. Hopefully it works. Otherwise we've got to move on to another solution and probably work late into the night. So we've got our 10 microfarad cap for the input voltage. We've got our 22 for the output. We've got our 2 wires, one for the input voltage, one for the output. We've got our adjustable voltage regulator, and we've got our 2 1 kilo ohm resistors we're going to use in a voltage divider setup to feed back to give us our correct voltage. We've got to start soldering this now and hopefully get this data back. Let's start with our input and output wires. Pin 3 was our input. Pin 2, the middle one, is our output. Actually, so's the back. We probably use the back output. Yeah, let's use the back. Resistor number 1 goes from our output, pin number 2, to our adjustment pin, pin number 1. These resistors looking a bit old. That's all I got. Resistor number 2 also connects to resistor 1 and the adjust pin. So with the capacitor, the short pin with the stripe, that's our ground pin, and this is our ground here, so we're gonna mash it together. Okay guys, we've got it all jimmied up. We've spent around $2 worth on electronics. Now we need to solder our input wire, our output wire, and our ground wire. Our 2.5 volt output wire needs to be soldered here. Now with the LDO, the voltage regulator needs a minimum input voltage of 1.25 volts greater than the output voltage. So it'll be 2.5 volts output plus the LDO reference voltage of 1.25. That equals a minimum input voltage of 3.75. Now the problem is the input voltage here is 3.3 volts. That's well below the low voltage dropout minimum rate. So it will not work here. So what we'll do to make it safe is we'll solder it directly to the 5 volt input line of the SATA connector. That means it should regulate quite fine, and we'll just ignore this input pin here. So these 3 pins here are ground. You can see a bit of a ground plane here, and these 3 rusty pins with this corroded cap, that's our 5 volt input. We'll use that. So I'll tack on to this pin here. We're just going to put some solder on it first. There we go, big solder ball. Both of them are ground pins. That'll be even stronger for us to solder the ground into it. And while I'm here, I may as well get some solder tacked onto our 5 volt input. Should be enough. This is what it looks like all soldered together on our test bench. Before we put it into circuit, I'm just going to test. Does it work? Are we going to get 2.5 volts out? And we do. We're getting 2.559 volts. Now keep in mind this is tested without any load, so that could change once it's got the load of the CPU running it. So let's solder it in now. We've got hardly any time left in the day. It's getting late, it's getting dark, and I need to get this data back. First thing to do is solder in the ground pin to the SSD ground pin. Now my soldering iron has gone on standby mode, so it's a bit cold. Come on, heat up. There we go. Perfect. Now we're going to wire our input voltage wire, the 5 volts from the SATA connector of the SSD. It's actually kind of difficult to get in here. done. Looks okay. And the last one's our output voltage, our 2.5 volts to power the SSD controller or CPU. Now this pin here is actually very small and the hardest one. But I think we got that there. Time to connect this to the SATA port, my SATA testing equipment. It's getting very late here and let's see if it works. Let's turn it on. And it is not working. I can see on my meter that it is not drawing any current. Let's figure out what's wrong with it. Okay, we're now in overtime now. The customer is calling me, asking for updates, and it is not working. I'm getting quite desperate now to solve this. The output pin 2.5, that is soldered correctly. Our ground pin 1, 2, 3, that's I think 12 volts. No, that's a 3 volt. Then these three are ground, that is correct. So 1, 2, 3, 3 volt, 1, 2, 3 ground, 1, 2, 3, 5 volt. We've soldered the input pin to the other ground pin. We need to move it over one. That's why it didn't work. Let's hope this does. So our homemade regulator wasn't getting any power. We're going to move it one pin over where it should be. Sorry about that, guys. It's getting late here and I'm starting to get a bit of brain fog with the pressure and the time that's running out. So, I mean, it worked on the test bench. We've soldered it into the correct points. Let's plug it back in. This is what our final repair looks like. You can see we've got our input capacitor, our output capacitor, our two resistors. You can see our wire trace here that goes to our CPU. That's going to power our CPU. You can see our little adjustable voltage regulator. It's just floating there in 3D space. And we're about $3 worth of parts really in. These are about 50 cents each. We saw $1.10, bit of wire, resistors, yeah, they don't cost anything. So we're around about $3 worth of local electronics repair shop parts. Okay, let's click the power button in 3, 2, 1. And bam, we can see current. We've got a ready signal on the SSD. We can now see that the controller is lighting up with the correct energy level, and we're seeing that on the thermal camera. This is great news. The electronics repair has worked. We do have a correct ID. We're going to run a test now to see what the health status is. Bear in mind this SSD is around 10 years old. But we're getting good feedback here. It is reading at a very healthy speed of over 200 megabytes a second. Down here we can see that there's a little bit of wear, but that's not a problem. It's running around 28 degrees Celsius and there's no other serious problems being reported. We'll let this test finish and then we'll move on to seeing if we can get data back for this customer and for this wedding that is due for this weekend. So there's all the customer's data. I've given them a call and let them know it's been successfully recovered. We're a little bit over time, but they're ecstatic to get the good news from us. If you need data recovery from a SSD that stopped working, you can mail in from anywhere in the world at zeroalpha.com.au. and we will get your data back at the lowest price. We also have a partner program for computer repair shops, and I'll see you guys in the next video.